once he came to Descartes and asked him to help calculate the probability of win or lose a game, because of that, upon that depends the value of stake. For example, you stake more money if you are sure that you will get maybe your probability of get this price is greater than, for example, 70%. Or if it's less than 30%, in this case, better to stake some small money. So actually, these probability, first steps of probability theory were based exactly on gambling and on the probability for events defined in finite sets. And this aspect we will touch, especially separately. All other continuous distribution functions, probability functions, and maybe some events, random variables, and everything will be touched in this or that way when we meet the statistics, elements of mathematical statistics. So after the class of today, we'll see what we reached. And if, for example, we have finished this first part of draft exam, including the probability problems, which are only 3 of them, we'll see if on Monday, October 15, we manage to pass at least 2/3 of statistical problems. Maybe I will include 2/3 of problems of statistics into the exam, midterm exam, which will be on Tuesday, October 16. Okay. Okay. Maybe after this not very nice introduction for you, let's start with and to finish with the logic theory, mainly working with temporal logic. Now let me please share my slides with you. Okay. Okay, so the last part of logic topic which you're considering. Once again, here we have some similarity, a lot of similarities with the previous part. So we're not going to stay in too much detail on some properties. Only we'll see again how it's possible to prove validity or unsatisfiability of different formulas and which relation they have to some other parts of logic. For example, we'll see that actually if your formula in temporal logic can be completely replaced, its parts, with some formula from propositional logic, and you are sure that the propositional logic is, this propositional formula is valid, so true for all interpretations, you may be exactly the same way, be valid, you may be sure that it's valid also in temporal logic. Why? Because actually the interpretation of formulas in models in temporal logic is exactly the same. If for all interpretations you have a true formula, then it is valid. But if your formula is valid in propositional logic, so if you substitute the terms of temporal logic in it, you have exactly the same situation, because the definition of valid formula for temporal logic is exactly the same. If for all possible interpretation it is true, then it is valid. But actually, difference only in interpretations, because from temporal logic, we see later, interpretation is a more complicated subject than in propositional logic, because we consider not only the values assigned to atomic formulas, but also the so-called worlds or states, because actually we'll see temporal because in time we can come from one state to another, go from this state sub 1, and go to state S2, then from S2 to S3, etc. Exactly this is the sense of temporal logic. We allow the movements in time in contrast to the previous parts of mathematical logic. Okay, so temporal logic is a formal system for reasoning about time. This is the key property. Temporal logic has found extensive application in computer science. This is especially usual for you guys, because the behavior of both hardware and software is a function of time. This lecture will follow the same approach that we use for other logics. Again, we define the syntax of formulas, how to construct any formula, and their interpretations. And then describe the construction of semantic tableau for deciding satisfiability or unsatisfiability. And you remember, if, for example, your negation of your formula is unsatisfiable, always false, it means your original formula is always true, so it is valid. And this is the usual way. So remember this refutation trick. You take the negation of your formula you're going to prove this valid and establish this is unsatisfiable. That's it. In this case, means the original formula is, of course, valid. True for all interpretations. Okay? Okay. So first consider the following example. Here are some examples of specifications that use temporal concepts, which are italicized. This is exactly what is completely new as compared to our previous two topics, namely propositional logic and first order logic or predicate logic. If a request is made to print a file, eventually the file will be printed. So please pay attention. The new term has appeared, eventually. It means for some time in the future. It's clear, not known this time, but in the future necessarily will be printed. But in some time, this analog of existence quantifier. Or the other sentence: the operating system will never deadlock. Never deadlock. Here, of course, you have the analog of for all. So for any time moment, your system is never broken. It's never broken. Is it clear? So this is analog of for all, but in time. The temporal aspects of these specifications can be expressed in first order logic using quantified variables for points in time. So t1, t sub 2, etc., t sub 3 for any t, etc. And by the way, this is the form in which we can write this sentence in kind of first order notation, first order logic notation. So for all t sub 1, if we ask in some moment t1, you ask print some paper or maybe several pages, then it implies there exists some t sub 1. T sub 1 is greater or equal than t sub t sub 2. T sub 2 is greater or equal than t sub 1, and at least exactly at this moment t sub 2, your paper was printed. So they will exist sometime in the future when your paper will be printed. So this is the typical formula of temporal logic. Or, for example, the second, for all t, never deadlocked. So for all t, not deadlocked at t. It exactly explains how in logical terms of temporal logic we explain this is this sentence that your system, for example, is never deadlocked. Of course, the use of explicit variables for points of time is sometimes awkward, especially since the specifications do not actually refer to concrete values in time, of time. So because of that, people maybe rare take, for example, your paper will be printed at 10:40 or at 11:30. Because of that, sometimes it's more convenient to use some indefinite concept of eventually or vice versa for all. So eventually simply means that at any later time, as the specification does not require that the file be printed within 1 minute or 10 minutes, etc. Temporal logic introduced new operators. They enable abstract temporal relations, like eventually to be expressed directly within the logic. Temporal logic are related to formal system called modal logic. By the way, we simply skip this. Modal logic is kind of intermediate chain in between first order logic and temporal logic. In modal, instead of eventually or always, you use words like necessary and there is necessary and possibly. Necessary is analog of always and possibly analog of eventually. But in temporal, we are not going to consider in detail modal logic, but modal logic was intermediate step, and many concepts and tricks were absorbed from modal logic by the temporal logic. Yeah, so a modal logic expresses the distinction between what is necessarily true and what is possibly true. Necessary and possibly true. For example, the statement 7 is a prime number is necessarily true because given the definitions of the concept of the statement, prime number, the statement is true always and everywhere. 7 is always prime number. In contrast, The statement the head of state of this country is a king is possibly true, because its truth changes from place to place and from time to time. We'll see later in some examples. Temporal logic and modal logic are related because always is similar to necessarily and eventually to possibly. Although temporal and modal logics first appeared in Greek philosophy, the vague concepts proved difficult to formalize and acceptable formal semantic for modal logic. And this formal semantic for modal logic was introduced first by Saul Kripke in 1959. There's a couple of words about Dr. Saul Aaron Kripke. He's an American philosopher and logician. He's a distinguished professor of philosophy at the Graduate Center of the City University of New York and emeritus professor at Princeton University. Since the 60s, Kripke has been a central figure in a number of fields related to mathematical logic, philosophy of language, philosophy of mathematics, metaphysics, epistemology, and set theory. Much of his work remained unpublished or exists only as tape recording and privately circulated manuscripts. Kripke was recipient of the 2001 Schock Prize in Logic and Philosophy. Kripke has made influential and original contributions to logic, especially modal logic, from which takes the root the temporal logic. His work was profoundly influenced analytic philosophy. His principal contribution is a semantic for modal logic involving possible words, now called Kripke semantics. But once again, his results for modal logic almost completely were absorbed and imported by the temporal logic. In 1977, another star professor, Amir Pnoueli, showed that temporal logic can specify properties of concurrent programs and that Kripke semantic could be adapted to develop a formal theory of the temporal logic of programs. In this lecture, we present briefly the theory of linear temporal logic. But once again, actually, majority of our concepts were more general than for logic. I will explain later what difference. So we'll consider actually not necessarily logic, linear constructions. But linear is much easier because we'll see later the future state is defined uniquely from the previous state. You have no branches. You have a straight line. S1, then after that S2, then S3, etc. So no deviations from the straight line. So much because of that, the mapping rho, which is later, is much simpler than for non-linear logic. For its application to specification and verification of programs, the computational tree logic, please see chapter 16 of Ben Ari, Mordecai Ben Ari, because we simply have no time for computational tree logic. This is a couple of words about Dr. Amir Pnoueli. He is living in Israel. Unfortunately, he passed away in 2009. Was an Israeli computer scientist and the 1996 Turing Award recipient. Maybe you heard about this name Turing. It's a well-known, Alan Turing was well-known English mathematician, also logistic of England, in England. And the Turing machine is one of the formal theoretical machines with which a lot of logical construction are tested. His works in computer science focused on temporal logic and model checking, particularly regarding fairness properties of concurrent systems. So please pay attention that model checking is the same as program verification. Verification of programs in computer science without starting the program. So theoretical verification of validity or solidity of your program. Now a couple of, we pass to the syntax of linear temporal logic. But once again, simply I put here linear because it's easier to pronounce and the notation is quite common. But actually, you sometimes see the propositional temporal logic, PTL, and definitions are exactly the same. Doesn't matter, it's linear or propositional as wider, meaning we allow some trees or some other constructions, for example, in the next example. In the next example, we'll see that not necessarily linear logic are defined by these concepts, but also general propositional temporal logic, PTL. The syntax is defined like the syntax of propositional logic, exactly the same. However, we have two additional unary operators. Unary meaning that we have only one argument of each operator. Not, for example, two like conjunction or disjunction, but only one argument, like exist or like always or like negation. So by this small square, we denote the concept of always in time. So it means for all moments in time. And this rhombus, we call it eventually. We pronounce this eventually. So this rhombus is pronounced as eventually. Okay. The discussion of syntax from propositional logic is extended appropriately. So formulas of linear topological logic are trees, so they are unambiguous, and various conventions are used to write. Yeah, actually, by the way, I'm not right here. I put here P because actually for linear temporal logic is not tree, a straight line of states. But for non-linear, the trees are allowed. Bless you. Trees, so they are unambiguous, and various conventions are used to write the formulas as linear text. In particular, the two unary temporal logic operators have the same precedence as negation. It's the same, so or existence or universal quantifiers. So these three objects have the same precedence or priority. So in case if you want to know that one of these operators is applied before some other, you must have a parenthesis. Put parenthesis in this case to indicate which will be first. Otherwise, it will be completed in the order of writing, in the order in which they are put in the formula. Okay. So let's consider the following example. They're simply formulas. We are not going to prove them or reject. Simply an example of syntactically correct formulas in a propositional temporal logic. So, for example, P and Q is even propositional calculus logic. So this is the propositional logic. All others are temporal formulas because they have involved these signs of always or eventually. For example, always P, or the third formula, eventually. It's eventually P and Q. It implies that eventually P. I think actually intuitively it's clear that it's true formula, yeah. Because if sometimes you have both formulas true, P and Q, it means that exactly at that time your P is true, because the conjunction is true only if both formulas are true, yeah. So it's quite evident that if you have eventually P and Q, so of course it implies that eventually P. In the same manner, it also implies that eventually Q. Or for example, the next formula, number 4, is a kind of formula, but you can always imagine that always P. It seems a bit without sense, but formally speaking, it's correct formula because you have applied this always to an existing formula. So you remember the same recursive construction of formulas is true for temporal logic as for propositional logic and first order logic. Yeah, and it's equivalent to for all always P. This formula is not so evident. Is it true or not? It said that eventually for always P, if or only if, for always, eventually P. Actually, it's even difficult to immediately understand the physical sense of this, because actually, if you have, for example, some formula always true P, so adding eventually, it does not change much its sense, because what means eventually always true? So it's formula always true. Yeah. However, if you change the order, so if you have eventually true, to think that always eventually true is not quite clear. Nevertheless, these are equivalent formulations. Or, for example, not eventually P and always not Q. Not Q. By the way, I'm not saying this is true or not true formula. Simply examples of syntactically correct formulas. They may be true, may be false, may be satisfiable or not satisfiable or falsifiable. However, they are lawful. So adjusted formulas, justified formulas. Okay. Some explanation, some comment that this last formula, not eventually P and always not Q, is not ambiguous because the temporal operators negation have higher precedence than the conjunction operator. So first we have to apply not and eventually to P, then we have to apply always not Q, and then combine them as conjunction. So because of that, no ambiguity exists here. But vice versa, for example, if you wanted to put that first we consider P and the second part of the formula, you have to take in parentheses, one parenthesis open and before P and closing after Q. The formula can be written this way to distinguish it from, for example, this one, negation of the formula. So once again, the formula in parentheses, not eventually P and in parentheses, always not Q, is equivalent to our previous formula. And this is the other formula. Strictly speaking, it may have different truthfulness than the previous one because it's different formula. We apply negation to a conjunction where our other operators are involved. Okay, any questions up to now before we pass to the semantic? All clear, I suppose, yeah? Estado Mexico, what's your opinion? It's okay for you?
Yes.
Great. By the way, how many of you are there? 1, 2, 3, 4, 5. How about half, yeah? Why so few people?
No,
15. Ah, so two lacking. Okay. So maybe because of great traffic in Mexico City. Huh? Okay. Now we pass to the semantics. So they are defining the validity or satisfiability or falsifiability or non-satisfiability of formulas. So informally, for always is a universal operator, meaning for any time t in the future. Precipitation in the future. So it means not we don't expand the time to backward. Only from this moment to the future. Where this rhombus is an existential operator, meaning for some time t in the future. For some time t. And now these two formulas from example 251 can be written as follows in a linear temporal logic. So for all, I mean always, if you request print, so it implies that at some time it will be printed. At some time it will be printed. It's always true. It's always true. Doesn't matter in what moment you ask for printing, maybe in several minutes or maybe in several hours, your document will be printed depending upon the file on the printer. Okay, and the second, that for always not deadlocked. For always not deadlocked. By the way, I think you can guess that actually the same De Morgan rules are true for this pair of operators. For example, this always non-deadlocked can be written the following way. Not rhombus deadlocked. So we are we have negation of that sometime it is deadlocked. No, this is not true. So we negate that rhombus deadlock. There is no sometime in the future when the system is deadlocked. Is it clear? So the same De Morgan rule also applicable to the pair of this operator. So here another the new difference and new complication arises because of exactly temporal structure of our logic. Interpretations of formals of propositional temporal logic are based upon state transition diagrams. So states are like kind of sometimes called also worlds. At each moment of time, you can consider a world. And this world comprises interpretations of your formulas. The intuitive meaning is that each state represents a world and a formula can have different truth values in different worlds. Now we'll see in some example in more detail. The transitions represent changes from one world to another. Now we give the following definition. A state transition diagram is a directed graph. To recall you, maybe not all of you met this concept in your previous education. Graph, actually, the concept but quite simple. It's simply a set of nodes and arcs. Nodes and arcs. Bless you. Usually, even graph may be depicted even in three-dimensional space, but usually people are restricted to planar graphs, so the two-dimensional graphs. You take, for example, your piece of paper or whiteboard and put at any position any number of nodes. They are absolutely arbitrary where you put them. Of course, they could be infinite number of these nodes, but usually graph theory is restricted to a finite number of nodes. And some, not all, not necessarily all, some pairs of nodes can be connected by arcs. By the way, it means, for example, that some node may have several arcs connected to other nodes. One node may be isolated completely, no arcs at all, this isolated node. Or maybe some couple of pairs of connected, but some pairs not connected. So graphs may be also connected or disconnected. Connected means that if you make, starting from any node, you can find a path, and path is the sequence of arcs, which are continuously move you from one node to some other node through intermediate nodes. So if you can find a path for any pair of nodes, such a graph called connected. But if, for example, you have two distinct graphs and no connection among them, this graph is called disconnected. And finally, the graphs also are divided to directed and undirected graphs. Undirected means that your arcs have no direction, so it means you can go this way or the converse way. So from now one node to the second node, or vice versa, from second to the first node. However, some graphs have arcs directed, so and an arrow showing that direction is only one way. It's like one way carril or two ways carril here in Mexico. So actually one lane or one-way lane or two-way lane. And in state transition diagrams, all arcs must be directed to show exactly where you come from this state. For example, from state S2, where can we come? To S1 or to S3 or to some other? Yeah, the nodes and states are the edges and transitions. No, nodes are states and edges are transitions. Each state is labeled with a set of propositional literals, such that clashing literals do not appear in any state. Clashing meaning that, for example, P and not P, it's impossible, or Q and not Q. So clashing literals don't meet. But the combination, other combination may be absolutely arbitrary. Let's consider the following simple example. Figure 251, a typical state transition diagram. Immediately, I would like to tell you that this diagram shows that our logic here is not linear. Because in linear, we can have, for example, S0, then the right arrow, S1, right arrow, S2, right arrow, S3, and nothing more. And such a kind of tree is simply impossible for linear temporal logic. It's example from non-linear or simply general propositional temporal logic. Is it clear? So for linear, we have only a straight line and direction of movement only to the right. Only to the right. By the way, for example, loops can be also programmed in this linear. You simply have, for example, in several states, you put some state which is equivalent to our initial state. It means we have a loop. We have a loop. Okay, so let's see in detail. We have how many states do we have here?
4.
Exactly 4 states. They are enumerated like S sub 1, S sub 0, the first one, then S sub 1, S sub 2, and S sub 3. Correct? Please pay attention that all arcs here, all arcs are directed. They're not allowing, for example, to move from S2 to S0. Vice versa, yes. From S0 we can come to S2, but not vice versa. From S2 you cannot arrive. Actually, you cannot arrive to S0 from any other node. So S0 is kind of initial state, and the system never returns to these states. Never. Yeah. It starts. All others may be, for example, from S2 you can go to S1, or you can come to even to and through S1 to S3, etc., and vice versa. But not from S0 you only leave it and never return. And please pay attention. At the state or world S0 we have 2 formulas valid, 2 atoms, P and not Q. P and not Q. And in S1 we have both formulas valid, P and Q. At S2 we have vice versa, not P and Q, not P is valid and Q is valid. So in other words, at S0 P is true, Q is false. And S1 both P and Q are true, and S2 P is false and Q is true. And finally at S3 in the final word, we have here that both P and Q are false. Is it clear? So this means exactly this. If you put not P, it means not P is true, which equivalent that P is false. Is it clear? Okay, and by the way, yes, you see that it's possible, some loops are possible. For example, you can, from S3, you can also return to the same S3. So sometimes it's called like a absorbing state. On the other hand, it's not, if you heard about Markov chains, that in strict meaning, here we have no absorbing state. Absorbing is like arriving, you can arrive to this state, but never leave it. So always accepts, but never allows to get out. Here we have no absorbing state because you can go from S1, you can leave S2, from S2 to S1, yeah. You also can leave S3. From S3, you can go to S2. So here we have no absorbing states. Okay. Yeah, so this figure shows a state transition diagram where states are circles labeled with literals and transitions are arrows. In modal logic, necessarily means in all the reachable words, whereas possibly means in some reachable words. If a formula is possibly true, it can be true in some words and false in another word, in some other words. Once again, a bit touch this modal logic to explain this links with the temporal. Example 2454, consider the formula A is the head of state of the country is a king. Explain once again difference between possible and necessarily. The formula is possibly true, but not necessarily true. Why it is so? Because if the possible words are different countries, then at the present time A is true for Spain, false in Denmark, because the head of state is a queen in Denmark, not the king, and false in France, which does not have a royal house at all. Yeah, even in a single country, the truth of A can change over time if a king is succeeded by a queen, or if a monarchy becomes a republic, etc. So this is the difference between possibly and necessarily. Temporal logic is similar to modal logic, except that the states are considered to specify what is true at a particular point of time. And transitions define also passage of time. You can, for example, consider that your S sub 0 as your state or your word at time 0, t equal to 0. S sub 1 at the moment t equal to 1. S sub 2 in moment t equal to 2. S 3 at 3 t equal to 3, and so on, and so on. Or for example, formula. Consider the formula A. It is raining in London today. On the day that it's being written, A is false, for example. He was written with no rain. Let's consider each day as a state and the transitions to be the passage of time from one day to the next. Even in London, always A, meaning every day it writes London, is not true. But eventually, rhombus A, meaning eventually London has a rainy day, of course, it's certainly true. Maybe it's even true for all cities in the world, except for one small city. I was surprised. Once I was invited to deliver a course of lectures at Honduras. And I landed not in the Tegucigalpa airport, but some other great airport like Seal, or I don't remember this, the North City. And we were passing one village. It was village when we were coming by car from the airport to Tegucigalpa. And this village is remarkable, people told me, professor of the Honduras University told me that it's remarkable and that this village is quite interesting. Every day in the year, rains is going there after midday. So every morning is clear, but every afternoon is rainy. And every day, 365 days, one by one, the same forecast is never broken. It's very interesting, special village. Okay. For this village, for example, if you say that always is rainy, this will be true. So square in this village will be true. Yeah.
So is there a kind of unique existential, like the rhombus A, like rhombus exclamation, like saying there will be only one rainy day in London?
Well, actually, you can imagine that. Probably could be said, for example, similar to exist only once. For example, could you put this exclamation sign? So a rhombus exclamation sign, it could be a sign, the property that exists, but only once. Of course, you can define it as you wish. So now we are ready to define the semantics of propositional temporal logic. Once again, in the presentation, I put linear TL in the headline, but actually now we have time to consider only more general, so PTL, propositional temporal logic. Because the interpretation is exactly the same for PTL or LTL, doesn't matter. And interpretation is a state transition diagram, and the truth value of a formula is computed using the assignment to atomic proposition in each state and the usual meaning of the positional operators. So, for example, if you consider our previous example, you can see that in state S0, P is true, Q is false, and so on. And you define if your formula is true or false in this state. A formula that contains a temporal operator is interpreted using the transition between the states. This is the formal definition of the interpretation. And interpretation I calligraphic for a formula A in a linear, actually, once again, it can be also propositional. Temporal logic is a pair. S capital is the set of all states in our diagram. And rho is a function. Actually, it's not function, relation. Right, relation, because we have several images, where S is the list of states, each of which is an assignment of truth values to the atomic propositions in A. And S, this is exactly the assignment. For each state, we have the function S sub I, which gives to all atomic propositions from our P the values of true and false. For example, in our case of diagram 2.1, we see that where is it? Yeah. For example, in our diagram, we have how many states altogether? 4 states: S sub 0, S sub 1, S sub 2, S sub 3. Yeah. And for example, for state S sub 0, S sub 0 can be considered as a mapping. So it provides to P, it provides value T, truth, and for Q provides value false. And S sub 1 provides the value true for both atomic formulas for P and for Q. S sub 2 provides the mapping. P is the value of P is false and Q is true. And finally, S sub 3 provides the values false for both atomic formulas P and Q. Yeah. And finally, rho is a binary relation on the states. Why binary relation? Actually, rho shows you the mapping or the where you can go from S0, from S1, etc. For example, for S0, we have which pairs? Let me please start writing, and then you continue. Oh, it has changed. Oh, no. No way. Okay, this is better. Okay, let me please copy this diagram to our piece of paper and start our exercises. Okay, please make share this. So please copy the diagram. So we have our S0, S sub 0. We have here P and not Q. I put simply bar for not Q. Okay, then we have the node S sub 1 with our P and Q both valid. Then we have the node S sub 2 with the valid formulas not P and Q. Okay, then we have the node S3 with a not P and not Q, okay? And we have the transitions from S0 to S2. Then we also have from S0 to S1. We have a transition from S1 to S2. We have the loop from S1 to itself. And then we have a transition also from S2 to S1. Then finally we have here transition from S1 to S3, from S3 to S2, and we have a loop from S3 to S3. This is our diagram. Now, let me please start writing rho. Remember that rho is our relation, which is from, of course, from direct product, from Cartesian product, S times S. So, rho, it contains which pairs? Let me please start, and then somebody comes here and continues to get extra points. I have a pair S0 and S1. Do I have it or not? Yes. Of course, we have a connection. Now, who would like to continue, please? Yeah, it was first. Yeah. Once again, recall me your name. Yeah, okay, bravo. Yeah? Okay, so let's continue composing our relational rho.
The sign between the S and the S is
people don't see it. Yeah, okay. Maybe. Yeah, okay. So, which next pair starting with S0 do we have? S2. Correct. By the way, immediately see that actually rho is not a function. Because for the same argument, S sub 0, you have two possible images, both S1 and S0. But this relation, for relation it's okay, but not for function. Okay, next. S1, S2, correct. And one S1. Correct, and one more with S1. Yeah, sure. Okay, now with S2. S2 is 1, correct. And that's it, yeah. And with S3. S3 S2, correct. And also we have a loop. So yeah, S3 and S3. Great. Absolutely true. So it's appeared to everybody. This is our relation rho defined completely by all elements. However, of course, you can also see the image. For example, if you, for example, want to see which nodes, which states are image of S0, you can write that rho of S sub 0 is the set of S1 and S2, correct? The image of S0 are two states because we have both connections from S1, from S0 to S1 and from S0 to S2. But there is no connection of S0 going to S3. So only S1 and S2 and so on. So for any node, you can find the image of your relation. Okay.
One question: the symbol that is between the S and the S is a times or a multiplication symbol, or is it?
Which multiplication?
S times S. Just out the row.
S comma S1 comma S1.
S comma. That's comma.
S comma, yeah.
S comma.
The one state, then the comma, and the other state.
No. I mean.
Where? This is the direct product.
Okay.
Because remember, this is because actually the images of your source and target are the same, state S. In this case, because of that, we have the direct product of S times itself. Okay, let me please return to our slides. Okay. Yeah. And by the way, sometimes to make it not so heavy, the diagrams are presented in with different notation. Sometimes if you know the list of all possible atomic terms, we can simply leave those who are true at each node. For example, in S0, we have P is true and Q is false. So we list only P, meaning that if no Q there, it means Q is false at this state. And S1, we have P and Q, both are true. Vice versa, in S2, we have only Q listed because P is false in S2. And S3 even left empty because both atomic terms, P and Q, are false at S3. Is it clear?
In this case, each state needs to use all the variables.
Yeah, it means, but for implicitly, it means that all variables may be. But it actually, usually, if you simply list all variables in all nodes. And actually, if, for example, some variable is not related to the node, so you should to decide something because otherwise it is not true, not false. So usually it's accepted that all variables are or true or false in all nodes. So variables must be present in all nodes, in all states. Yeah, so by displaying an interpretation graphically, the states are usually labeled only with the atomic proposition that are assigned true. This is the previous figure. If an atom is not shown in the label of a state, it is assumed to be assigned false. Since it is clear how to transform one representation to the other, you can see now lectures any one, which is more convenient. Okay. Yeah, a binary relation can be considered a mapping from a state to a state of set of states. For example, rho, like a mapping from S to all subsets of S. So the relation S1, S2 from rho means that actually we're writing that S2 belongs to the image of S1. S2 belongs to the image of S1. Belongs because actually the image need not be unique. For example, you see in our case, a row of S sub 1 is S2 and S3. Yeah, S2 and S3. So because of that, we can write that S2 belongs to row from S1 and S3 also belongs to row of S1. Okay. And this is the complete list also of our true and false values for each of the terms atomic terms in each node. For example, in S0, P is true, Q is false. In S1, P is true, Q is true. At S2, vice versa, P is false and Q is true. And at S3, both are false. Both are false. In the images, yeah, I also forgot about S1. The row of S1 contains 3 symbols. S1 because I have a loop from S1 to S1, S2 and S3. Row at S0 is 1 and S2. A row of S2 only S1, because we have only one link emitted from S2 and coming to S1. And from S3 we have 2 leaving links. I mean the loop to 3 and S2. Now the definition of truthfulness, truth value. Let A be a formula, and once again, it's possible to put here also P, not necessarily only L. P, propositional temporal logic. And the value V, and we denote below 2 sub-indices. First I, calligraphic, and then S, because it's quite clear that the truthfulness of the formula can be different in different worlds and different states. So it has to put interpretation and S. And interpretation, by the way, remember, it's actually the, it is exactly the pair S, total S, and all row, and row, also row. So the truth values of A in S is defined by structural induction as follows, as previously, as we always did for previously in propositional logic and first order logic and in any other logic, usually the same construction is used. So we only defined the truthfulness for atomic parts. And then your combinations by different logical operators, they inherit the truthfulness according to the properties of these operators. For example, if A is simply P from P calligraphic, the P calligraphic mean all our atomic terms. So if P is from atomic term, then exactly the V of this A coincides with the value of truthfulness at state S, because it may be different. Remember, for example, P is true in S0, but is false in S2. So it means that your formula containing only P will be true at S0, but false in S2, correct? Because we have here, remember, we have this situation. So here, for example, P is true at S0, but false in F, I mean at S2. So the validity of formula also depends upon where, at which world, at which node you are. Exactly because of that, we have 2 sub-indices. First, interpretation, and then S. Interpretation, and then S. Interpretation I means the set of all nodes and the function of row of transition. And the values of truthfulness are given at each S. Next, if, for example, A is a negation of F prime, here F prime may be already some previously constructed formula. So we are going by induction. We add one more operator, negation. Then, of course, we have simply change of the truth from true to false and false to true. For example, if, for example, A prime were false in our interpretation, so A will be true and this interpretation. And if and only if means that vice versa. If, for example, A prime is true, so in this case, A will be false. And then again, the usual transition from when we add operator or, it means, for example, if A is A prime or disjunction A double prime, then the value of A is true if and only if either A prime is true or A double prime is true. But only in one case when both are false. In this case, A is also false. And similar for other Boolean operators, for conjunction, for XOR, so exclusive OR, etc., etc. For any operator, you can do the same like in our propositional logic. Yeah, here it's because we have new operators, we have to describe truthfulness for these new symbols, for square and for rhombus. So if A is a formula structure, always A prime, always A prime, then the value of A is true if and only if, please attention, for all states reachable from S, because we are talking about S, so for all states reachable from S, this formula must be true. Not for all together, but only for the images from S. For example, from S0 you can go to S1 and S2. So if your formula is true for S1 and S2, then it will be true also for S0. For all means that for all coming from there. And finally, if A is eventually A prime, then it is true if and only if this formula is true for some, not for all, but at least for some state S prime from the image of S. For example, if you have eventually, so for S sub 0, if it is true at S1 but not true in S2, it's okay, it's eventually true, but not always true. And as previously, consequence, so S implies the interpretation I implies U is used for A's true interpretation I at the state S. Yeah, so when I is clear from the context, it can be omitted, simply putting S implies A, if and only if the value of A at state S is true. Now a couple of examples more. Let's consider the truth value of the formula, this formula, always P or always Q for each state S in our figure. Now remember, we have the image from S0 only two states, S1 and S2. So we change this formula only for states S1 and S2. And remember that actually, because Q is true both at S1 and S2, so it means that actually, because we have conjunction, it's enough that at least one is true, or for always P or always Q. But for Q, we have indeed always Q, because we have only two images from S0, S1 and S2. And because Q is true in both, so it means that this formula always Q is true. And by the semantics of disjunction, it means that whole formula also is true. Because at least one is true, so it's okay for the disjunction. So please pay attention. Of course, for linear logic, it's much easier because we have only one image. And then by induction, we have that if it's true in S0, it's true in S1. Then true in S1, it's true in S2, etc., etc. So actually, induction is also quite similar for linear temporal logic. Now for S1. In S1, we have a different, because remember in our S1, we have that P and Q both are true, but S1 has an image, S1, S2, and S3. And at the 3 and the 3, both are false. Q is false and P is false. Yeah. So this is the problem with S3. So for S1, it means our formula, or for all, always Q or always Q, always P will be false. Because the problem that Q is false at S3 and P also false at S3. So formula, neither formula always P or always Q is false. So it means that in our case, S1 does not imply the formula always P and always Q or always Q. Is it clear? And finally, for S2, row at S2. For S2, yeah, it's easy because S2 has only one image, yeah? From S2, we can only go to S1. But at S1, both P and Q are true. Because of that, always P or always Q is also true at S2. Is it clear? Because from S2, we have only one image, S1. And S1 is very favorable for both P and Q. And finally, S3 has in its image also S3. And vice versa, S3 is very unfavorable for both P and Q. So because of that, at S3, this formula is false. Yeah. So we have this example how we verify the validity or satisfiability of formulas containing the temporal operators, always and eventually. Yeah?
S1 it was false and for S2 is true.
For S1 false?
For S1 is false? Or
Yeah, for S1 because exactly we have S3 in the image of S1. And 3 is this.
is true.
Yeah, but for 2 it's okay because we have S1. Yeah, because we only one image S1, but in S1 both formulas are true. Now the same similar concepts of satisfiability and validity. Once again, is similar as to propositional logic or first order logic. Satisfiable means that it is true sometimes. Sometimes, maybe not always, but sometimes it's true. If it's never true, it's unsatisfiable. So the opposite to valid. Valid, vice versa, when it is true for all interpretations. For all interpretations means for all S and for all I. The definition of semantic property in PTL is more complex than in propositional or first order logic because an interpretation consists of both states and truth values. Both states and truth values. So the definition. Let A be a formula. So once again, please I see your pattern. Usually I had here P, but somebody I have changed to L, then I understood. No, it's also true for P. So not only linear. Linear is trivial, only straight line. Definition 255. Let A be a formula in propositional temporal logic. So first, A is satisfiable if and only if there is at least one interpretation, I, containing all states and the mapping of rho, transition mapping, for all, and a state S from S such that you can deduce the formula A from state S. So this is true at all elements of image of S, image of S. So it's satisfiable. But so it's at least once, for at least one interpretation, and for at least one state S. That's enough to be satisfiable. However, a stronger definition, A is valid if and only if for all interpretations and for all states, S must be satisfiable for, A is deduced from S. And in this case, of course, if simply put without any S in the left-hand side, simply A is always true or valid. Always true. Again, you can see that the example from the formula or always P or always Q from our example. And we see that A is only satisfiable because, for example, for S0 it's okay, and for S2 also is okay. However, the formula is not valid because it is not satisfiable for S1 or because not an S3. So not for all states, and not for all interpretations. So it is satisfiable but not valid. Now let's solve the following exercise. Actually, it's quite easy exercise, but still needs some argument. It's a very important result, which allows one to save a lot of time, work and hard work when proving the validity or anti-satisfiability of formulas in propositional temporal logic. Show that any valid formula of propositional logic is a valid formula of propositional temporal logic, as is any substitution instance of a valid propositional formula obtained by substituting PTL formulas uniformly propositional letter. For example, you can see the following formula. It's propositional temporal logic, PTL. Always P implies always Q implies always P. But it is valid, always valid. You need not check for any states. Doesn't matter how many states. The structure is absolutely not important, because if you substitute this always P by A, and always Q by B, we have the following formula. A implies B implies A. But this formula is always valid. By the way, let us check now with this exercise. Who would like to get extra points that A implies B implies A is valid? It's easiest because it's propositional logic, the first our topic. Who can try to solve this? Yeah, please do it. So let's prove that the formula A implies B implies A is valid. And this will mean that actually our temporal logic will also be valid. Doesn't matter structure of our tree or some other system of states. Okay, now let me please first write this formula here. A implies B implies A. Okay, and now let me please switch to the screen.
Was alpha, right?
B implies A. So B implies A. So let's first take the negation of this formula. Yeah. What is negation of this formula? Yeah. So negation of A implies B implies A. Close the parentheses, both parentheses. Now put equivalent sign, equivalent, 3 lines. And please remember again that the negation of implication is very simple. It's our A and not negation of the.
Teacher, we can see the.
Excuse me. I forgot to change it. Yeah, excuse me. Now do you see it?
Thank you.
Yeah, a bit here to see this negation.
Negation.
Why doesn't? Yeah, negation. Yeah. Equivalent to A, correct, and negation of the second implication. Okay, great. But now let's apply once again. Negation to implication. So continue equivalence. Continue equivalent. Does everybody see this equivalent signs? Equivalent. Now put it here. And B опять. Negation of A, correct? Now, even without constructing any tree, we see we can put cross, yeah? Because it's impossible. A and negation of A. Even you can, for example, we can do some to be absolutely correct. Put first alpha and put the list A, comma B, comma not A. And of course it's cross. Put cross below because it's impossible. Yeah, so we obtain negation is unsatisfiable. So our formula is valid. Is valid. Let me please mark your participation. So once again, your name is Tejeda. Yeah? Okay. Thank you. Yeah. Any questions or doubts? We have just demonstrated that the formula A implies B implies A is always valid. Doesn't matter. Because of that, it's very nice because we have here replaced this always P by A, always Q by B, and you obtain the following, that our original formula, let's return to our slides. Yeah, it means immediately we need to prove now with all our state, doesn't matter the structure, because simply it is for any interpretation, we have the same result. Is it clear? So when a temporal logic formula repeats the structure of some propositional logic formula, it not necessarily even consider different states, etc., etc. If your formula replaced by letters provides a valid formula for propositional logic, it will be also valid for temporal logic always. Unfortunately, of course, this is a rare case. It's quite a rare case because for real problems which are essentially use the time, it's almost never true that you can replace your temporal operator by some simpler formulas and obtain a valid formula. It's quite a rare case. However, you should not miss this rare case. Of course, there are other formulas of propositional temporal logic that are valid because of properties of temporal logic and not as instances of propositional validities. So it's quite rare case that you have immediately from some independence of time. Okay, when we prove the validity of two formulas directly from semantic definition, the first established a duality between for all and sometime, eventually. And the second is distribution of for all over implication, similar distribution of, for example, quantifier of universal over implication. Exercise. Now, maybe we'll make a short break because we have more force, and then we try to solve together with you this exercise. Okay, so 10 minutes break, please.
O sea, puedes cortar, o sea, virtualmente cortar la mitad del lado y decir, ok, voy a respetar este corte para este lado y este otro corte para este otro. Y así generas un nuevo individuo. Y el individuo es un algoritmo de corte. Ajá, o sea, de cortar. No es un árbol. Sí, o sea, al final esto va a terminar convergiendo a algo que o sea, si hace un árbol. Sí, pero, o sea, lo que traspasa no es el árbol en sí. Los cortes. Ajá. Sí, y eso pues ya se puede.
Professor, one question. Professor, can you hear us?
Yeah, sure.
Oh, okay. We were wondering, for example, if in the previous example where you have always P, then implies that always Q implies always P. What happens if we have eventually instead of always?
In the previous example?
Yes. For example, we have always P implies that eventually Q, for example.
For example, here instead of in this slide, yeah, I mean instead of always P, we had eventually P, and here eventually P, yeah. Yeah, absolutely doesn't matter. If it's possible to replace all your operators with the formulas without any temporal signs, in this case, if this formula is valid, it's okay. So if here ahead, eventually P implies eventually with the same structure, you obtain A implies B implies A.
But they all have to have the same temporal quantifier, right?
What happens if we have a mix of
A, B, and A have no any temporal quantifiers. Only A is some simple formulas. Actually, it's true because if you remember once again, if formula A implies B and A, it's true for any interpretation. And so because of that, if you can replace all temporal operator with some formulas without temporal operators, and this formula without operators is always true, is valid, it means your temporal will also be always true for any interpretation. Because it's simply structure of the formula is such that its value does not depend upon the interpretation. Is it clear?
Oh,
So
yes.
for any value, if A is true and B is true, this formula is true. If A is true and B is false, this formula is true. Vice versa, if A is false and B is true, this formula is true. Finally, if both are false, we again true. We have again true.
Okay.
Okay.
So
Thank you.
for any, you can imagine that also in your temporal, you have many more interpretations. But actually, because the validity of the formula A implies B implies A does not depend upon the truthfulness of either A or B, it means with the same will be for your temporal formula, because its truthfulness by structure does not depend upon the validity of your parts. Any part have truth or false, you have always true. A implies B implies B implies B implies A. Yeah, it's always true. For example, if both A and B are false, you have B is false, so the A is false is enough. If A is false, the implication is always true. Correct? Doesn't matter which is B implies A is true or false. Absolutely doesn't matter. So in any case, if it's possible for you to replace any temporal containing formula by some formulas without temporal operators, and the resulting propositional is always true, you may be sure that your original formula is always true again. Because actually, this is the strong feature of valid formulas in propositional logic. They are always true independently upon the truthful values of each part. This is a very strong value.
Thank you.
The same as in any interpretation for temporal formula.
Thank you.
So this is interchangeable only because of the structure, right?
Yeah, so if you have reduced by substitution, you can reduce your complicated formula to a simple propositional formula, which is always true. You may be sure that your complicated formula is always true again.
Okay, thank you.
But the validity of this propositional formula does not depend upon the truthful values of each parts. Doesn't matter if A and B both are true, or both are false, or A true, B false, vice versa, A false, B true. This formula is always true. This is a very strong property of validity of a formula.
Okay. Thank you, Professor.
When you have a negation and the same value of the same branch, right?
No, I mean this formula A implies B and B implies A. It is true for absolutely all possible pairs, A and B. True, 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 false, false, true, false, false. In any situation, it is true. Exactly, if you substitute this A, B, and A by some other operators of temporal operators, it does not affect the truthfulness of the formula. Because again, because its truthfulness does not depend if you, for example, for all P is true or false. It doesn't matter, absolutely. For example, if for all P is false, immediately the implication is false. Vice versa, if always P is true, so P is always true. In this case, you see that your implication will also be true because in parentheses you have implication. Again, it depends upon the values of for all Q. If Q is always true, then we have both implications are true. As we have true implies true, it's okay for implication. If for all Q is false, then again we have the implication is always true. And again we have true implies true. So once again, if you change, you simply take this truth value table and apply all your values for A and B, you have always true. So if you can replace these letters by some very, very complicated operators, but still the structure is the same, you may be sure it is true for any interpretation. This is a very strong property. However, unfortunately, it's not often. You can reduce your formula to some also always valid propositional formula. It's a very rare case.
Anotando mis resúmenes, ahorita te voy a resolver.
Lo voy a subir primero.
Ya lo vi.
Error.
No, de por qué los exámenes. Es el resumen del resumen de la sexta lectura.
Para pasar las cámaras, las palabras, puros sinónimos.
Lo pongo en traductor Google en inglés y después lo pongo
Mira,
en
la-
traducciones.
A ver. Pero ya lo subí. Me vaciaron.
¿Sabes por qué eso?
Oye, ¿por qué puedes ver los attachments que tengo en las notas? Lo que te enseñé ayer.
No lo cambian.
No lo cambié.
Un nombre gordo.
Los no están en igualdad. O sea, los tengo por eso te todo. Los puedes ver.
O sea, no hay revisión, pero desde así tiene que.
Yeah, exactly. This question I answered just now to. Yeah, because it's absolutely doesn't matter. You can get very complicated three lines operator here. The same here, the same. But if it's possible to replace it by a valid formula, and this is B implies A is always valid. Yeah, because it's true for it's true. You can check by any truth table. You can substitute. We have always true. So it doesn't matter. But exactly for interpretation means that for any values of these elements, true or false. So no difference, absolutely. If this formula is always true, so this will also always true. Yeah, if it's possible for you to reduce the valid only to valid formula. For example, this valid formula where sometimes true, sometimes no. For some truthfulness of A and B true, for others no. It's impossible to apply. So no use.
Una casualidad. Es que más bien ahí, o sea, ahí es un statement antes, o sea, el punto es de que al final, o sea, después de todo, termina dejando los regalos, o sea, ese es como el statement. Entonces lo puedes hacer de varias maneras, puede ser por ayudar, puede ser puede ser por... Sí, entonces ahí yo que visita para las casas. No, para los casos de los visitantes de carbón los niños malos no les deja carbón, tradicionalmente les deja carbón. Yo conocí el Krampus.
Pero el estacionamiento
Si era niño llorado.
¿Y tu colegiazo?
No, esa paga con lágrimas.
Te pagas con tiempo, que es más valioso.
Ay,
Pero te cobran
qué romántico.
¿Cómo era? Poesía para física para poetas.
Güey, es un libro, güey.
Yo voy a escribir otro poesía para física.
Es que esta madre es pura mamá. Te cagan así a gente.
Luego el
Existe, te digo que es pero
complicado.
malo,
La abuela
está
le
malo,
dice,
güey.
todo esto va a ser tuyo.
Bueno, no está
Todo
tan malo.
oye, luego se le beben un
¿Qué?
polito. ¿Cuánto dinero tiene esa
No,
gente?
¿Cómo se llama?
física para poetas.
Después de luego.
Sí, es física para ciencias sociales.
Ah, es que visité.
Pero no se lo recomiendo. No. Está mejor la película.
La parodia.
Está mejor la adaptación. Está mejor
No sé, pero la
No, yo tengo que traigan regalo. No, yo lo hago. Ah, lo bueno. El día de la bandera que te vamos a
una pavota.
No, sería al revés. O sea, eso es lo que le dejas a él.
Todos los días.
Y con eso comprobamos que con la gente se
Es más como el diablo, que más polvo.
Con chido, pero con el corriente. Con chido, pero buscar esos amigos.
Ahí dice un TR de pronombre.
Aquí se hace eso.
Sí, pero.
¿Así ahorita?
¿Cuál es el eje?
No puedo reír.
Y luego el capítulo de South Park, que se ve.
Es que se ve. Depende de todo, ánimo se puede vaya para un lado para
no, obviamente no.
Me encanta que hay una playlist de Spotify que se llama música para bailar como los malos, algo así.
Sí, como esas imágenes de Facebook que se hace su ángel.
Okay, so let's continue because we have not too much time left for our class. So you are invited to prove theorem 13.14 from the book of Ben Ari Mordecai. Sometimes it's called also duality theorem. And you see, actually, it's very similar to the Morgan law, so applied to the quantifier. So in other words, if you transform negation of eventually, negation of P is the same as always P. That's quite intuitively quite clear. If you are negating that sometimes P is wrong, it means P must be always true. Yeah. So always true is the same as not that sometimes wrong. Not that sometimes wrong. Okay, now let's prove, because we have if and only if, yeah, equivalence. We have to prove both directions, both ways. Let's first prove necessity. So we'll establish that actually the implication that always P implies not eventually not P is true. And we have two ways to prove. First, let's prove by simply logical arguments without even semantic tableau. Because sometimes with temporal logic, it's easier than using this formality of semantic tableau. Indeed, assume that always P holds, but the negation of eventually not P holds. So simply eventually not P. How can we obtain the contradiction of these assumptions? So we actually are proving by contraposition. We assume the opposite, that even though for all P is true, but the conclusion is not true. So sometimes we have not P. Of course, intuitively, it's quite evident how you continue. You say, okay, but sometimes not P, it means some time or moment of time, for example, T sub 1, we have P is wrong. Yeah? But it evidently contradicts that for all T's, we must have P's true. However, in mathematical logic, it's necessary to go along the formalities. So you should write the following. Okay, let me please now switch to the to our piece of paper. Okay, so I write the following. Okay, what does it mean? What does it mean that for all P is true? Also the same as true, yeah, is true. What does it mean? Formally speaking, it means, so it is if and only if, for all interpretations, so it means for all S from S capital, yeah, from all S and capital, and for all, say, S sub I from rho of S, so for all states where we arrive from S, we must have that Si of P is true. Si of P must be true. So for all interpretations, for all states S, and for all images from this other states you can come from S, you must have that Si of P must be true. Correct? This by definition of always true for all interpretations. And remember, the interpretation include both list of states and also the list of transitions from each state S small, for example, to other states of this list of S capital. Okay. Now we are going to come to the contradiction. Indeed, because on the other hand, what does it mean that eventually not P, not P? It means, if and only if, that there exists some S bar, for example, from S, I denote by S bar to distinguish from some others. So some fixed S bar exists from S. And also there exists such some S, say, J from rho of S bar, Sj from rho and S bar, such that Sj from P is false. From P is false, correct? Because not P. So Sj of P is false. But now it's quite evident that this contradicts our first assertion. Because for all P, always P, for always P, it means that for all S from S and S bar is from S, yeah? And for all Si from rho S and our Sj is rho from S bar, we have the contradictory. It must be true, but it is false. Contradiction. And this contradiction immediately implies that our assumption was wrong. So if always P, then not eventually not P. Is it clear? Exactly by contradiction. Sorry?
Right?
Yeah, so eventually not P means that there exists some S bar from S and some Sj from rho of S bar such that Sj of P is false, which evidently contradicts our assumption that for any S from S and S bar is from S, and for any Si from rho of S and Sg is some from rho of S bar, we must have Si is true, but we got that Sj is false. This contradiction immediately implies that actually you are wrong and the assumption was wrong. So actually, indeed, always P implies not eventually not P. Not eventually not P. And again, the same can be done by no, actually, it's impossible now to do with the semantic tableau, because semantic tableau we have to use the negation of this implication. Oh no, maybe let's try semantic tableau indeed. So let's do the same but semantic tableau. Let's consider the negation of this implication. So our negation of for all always P implies not eventually not P. Okay, so let's try to prove by a semantic tableau. We consider the negation of formula, and they are going to show that this formula is unsatisfiable. If it's not satisfiable, it means our original formula is valid. Correct? Okay. We can use, I'm not going to use, for example, this, we don't use the properties of eventually and always, but we can use the property of negation of implication, yeah? We remember this can be rewritten, it can be written like always P and negation of this negation, yeah? So we simply put eventually not P. Eventually not P. Correct? This according to our well-known properties of negation of implication. Correct? So the premise and not conclusion. And the negation of conclusion. Now using this structure of alpha structure, we put alpha. And we have here always P, comma, eventually not P. Eventually not P. And now we can apply again the similar to first order logic instantiation. Instantiation, yeah? So it means that for some, you put it like also like by dot line, instantiation. And exactly here, we use our instantiation as follows. We select some S bar from S, and select some Sj from row of S bar, correct? And so we have here that we select some S bar from S, it's instantiation exactly, because it says exist sometimes, and this for all time. So we can select the S bar for both, for exist, for eventually, and for always, yeah? Because always includes alls. For this is some exist, some S bar. Exist some S bar. And for this includes all, so for S bar too. And so here, for this we have, for one we have, and also for some S, say J from S bar, I mean belonging to S, belonging to row is a sin. Sj belongs to row of S bar. We have the following. On one side, we have that P, and the other we have not P. Not P. Yeah? Because in other words, it can be written that so Sj of P is true and Sj of P is false. And of course, this can be crossed out. We have the complementary pair in this leaf of this tree. Is it clear? It's absolutely the same. Okay, any question or not?
What's the sign about the Sj?
S bar from S capital, comma, Sj, like Sj belongs to row of S bar. Sj, yeah. Exactly, this consists in instantiation. We select some state and some Sj from the image of this state. So where you come from S to S bar, from S bar when we come to some Sj. And in other words, it can be written that P is the same as to write. It's the same as to write that Sj of P is true. On the other hand, this not P means that Sj of P is false. So we have simultaneously true and false, which is crossed out. This if is crossed out means this formula is insatisfiable, that the original formula is valid. Okay, now I would like to invite the people to do the following. No, this is the home site. This is homework, okay.
Let's do the homework.
So the converse, to prove converse direction is homework 2.5, the first exercise, 253. yeah, 3 because we already used exercises previously 251 and 252. Okay, so okay, but anyway, let's indeed maybe try it together with you, solve this exercise 253, and then you repeat your solution in the homework. Yeah. So anybody who would like to, yeah, please do it, Kevin. Let's prove in both ways. You first prove by this only logical arguments, and then somebody else will prove by the semantic tableau. Okay, so let's please now switch again to the camera. You simply take this, we have to prove the converse. So vice versa, that this implies that. Not eventually not P implies always P. So you have to prove that. So now we're going to prove the following formula that that not eventually not P implies always P. Always P, correct. So now first let's prove by the argument. Let's again by contraposition. Suppose that its implication is false. So suppose that this is true, but this is false. Okay, so suppose first, let's write. Suppose that not eventually not P is true. Like in E. Suppose that not eventually not P is true. It means, of course, that the without this not, that that the eventually not P is false. Yeah. So it means that eventually not P is false. Is false. Yeah. Okay. Now, what does it mean that eventually not P is false? It means that for all interpretations S, for all S from S capital, it means you can put like if and only if, like this. Yeah, it means interpretation that for all S small from S capital, from S capital, and for all Si, for example, for all Si belonging to rho of S, rho of S, correct. So actually it means that not P must be false, yeah? Must be false. Just a moment, let's do once again. Eventually not P is false. And eventually P, yeah. So actually no, vice versa. That better say that for all S and for all Si, P must be true. So never it is false, never, yeah? It is never is false. Because eventually not P is false means that not P is always false. Is it clear? Yeah, because it's negation of exactly of that. Sometimes not P is true. No. So it means that for all S and for all Si from all S, actually P is true. So Si of P is true. Si of P is true. Yeah, so we have obtained the correct, but it's exactly what it means by always P. It's the same, there's always P. Always P. And that's it. Now let's prove the same, but now with the semantic tableau. Let's take the negation of this implication. Mm-hmm. Mm-hmm. Okay. Now let's first describe by the equivalence. Is equivalent. Remember, negation of application means our premise, so not eventually not P, and all negation of always P. Correct. Negation of always P. Okay. Now let's continue. It's our alpha type operator, so we can put down the vertical line alpha and simply write, repeat these formulas. Not always not P and not or not negation of always P. Okay, so now I think we have to consider two cases. Let us see once again. So negation of P. Well, I think we have to do again here instantiation. So let's put this dot line, instantiation. Instantiation. And now again we have to consider some S from S capital, S small. Consider some S of S capital. And some Si from row of S. Okay. Such that, because we have this not always P. It means that in some S, we might have that P is false. Yeah, P is false. So in this case, the second gives you P, simply P. Gives you P. Okay. And the first formula, let's see. Because negation of eventually and negation of P, it means that for all we have not P. So we have, including for this S, we have also not P. We have not P here. Comma. Yeah. And of course, this is our, again, contradiction. We can simply put a cross. So we have a complementary pair in this leaf. So this leaf is invalid. Yeah, so we have obtained now that also by semantic tableau that the negation was false. So the original formula is valid. Negation is unsatisfiable. So original formula is valid. Is it clear? Okay. Any questions in Estado de Mexico? Is it okay or not? It's okay with you? Okay, great. Yeah, please.
P is from not always P?
Not always, yeah. Not always. And we exactly selected, but not always. There exists some S bar, for example. We can put even S bar here. But S bar, and this is from S bar. If not always, so exists some S bar where P is full. The P is not always P.
Always P means that.
Just a moment. If not always P, we exactly select this is not P. It must be not P here. Not P here. And then here vice versa. So because we have not always not P, we select exactly this P bar that will be P. Exactly, this will be P bar is equal to P. Yeah. Yeah. So we have P, not P. But anyway, we have this complementary pair, and it means that our original formula was valid. Okay, thank you. Okay,
You're
please.
testing the other side, or that's the same time?
Sorry?
You were testing the other side, or that's the same time? It was just a sign?
Yeah, because it's selected, because it's not always. You select exactly which one when it's not always. Okay, please mark your participation, Kevin. Okay, and now we think we finish with the logic completely. Thank you. This is again reciting our homework 2.5. I will open also this assignment for this. In next exercise, you should by yourselves prove theorem 1315 from Ben Ari. So always P implies P. Q implies also that always P implies always Q. Okay, and that's it. Now we, if no questions or doubts, we pass to solving the draft exam. Solving the draft exam. Mm-hmm. Draft exam. Okay. Let me please open the draft exam. Does everybody see the draft exam? I call it draft exam October say until 15 because part of this draft exam will also explain to you on the end of the class of Monday of October 15. So for you to be ready to write your exam on 16 October. So we have this. We are going to share the solution of these draft problems from between today and the last part of the class of Monday, October 15. So we try to solve today as many as possible problems, and the rest will be solved on Monday. If we be very much behind with the statistic, maybe indeed I will cancel statistics. We only include 3 topics in this case: the set theory, logics, and probability theory, and that's it. Okay, so first exercise, which is based exactly on the following construction. Exercise 1.1. This is from set theory. Suppose 50 computer science students are polled to see whether or not they have studied French or German, yielding the following data. 25 studied French, 20 studied German, 5 studied both. We have the 4 questions here. Find the number of students who A, studied only French, B, did not study German, C, studied French or German, and finally studied neither language. To solve this problem, let me please do the following. Let me please switch to the our camera. And it's quite useful in such problems first to draw a picture. So it's quite common to select this rectangular as the universal set containing all 50 students. Okay? Now it's quite common also. Let's denote by set A, or better set F, those who studied French. Okay? Next. And set G, those who studied German. Is it clear? So according to our data, it means that the amount of people studying French is equal to how many? 25, correct? Okay. Amount of students studying German is 20. And also, we are given the amount of intersection set, yeah? Though he studied both languages. So this intersection, denoted by F, intersection with G. Its amount is how many? 5 students. Yeah. So now we can answer the questions one by one and quite easily. A. Question A. How many students studied only French? Only French. What do you think? How we can find this number? Yeah, we simply find this area. We need to find the area of the difference. F minus G. F minus G, correct? So those who studied French but did not study German. And of course, according to our data, it's equal to the amount of students studying French minus amount those who studied both languages. Correct? Yeah, please.
Why isn't only the amount of F not 30? Because
Of F, not 30, but according to our conditions, we have 25 studied French.
Yeah, because if you add all of them,
According to our condition,
if you add all of them, it's not 50. There are students that don't study any languages.
we don't understand the question. We have this data. 25 students studied French. Why you? What do you mean in 30? What do you mean by 30?
because half students are studying both.
Yeah, but those who studied both languages, they included in two sets, both in F and both in G. So this is the exactly intersection. Who studied both languages, intersection of sets F and G. Is it clear? And we are given that the amount, the power of this set, the quantity of elements of the set is 5. Okay, all clear? Okay, so we have immediately it's equal to 25 minus 5 and is equal to 20. So this is the answer to the first question. Okay. By the way, in the end of this slide, we have a file. We have all our solutions are listed. You can read again our solutions after the class. Okay. Okay. Now question B. B. How many students did not study German? Did not study German. In our picture, it will be efficiently it will be the complement of set G, correct? Those beyond G. So actually will be the amount of U minus G. U minus G. Or you remember actually sometimes it denoted as complement by bar. G bar, the complement of G. And because we have no units included, we have 50 minus 20, correct? Because we have at least G is inside the unit of students, all accounting 50. And we have in this case 30. 30 is a number of students who did not study French. Any questions or doubts? The Estado de Mexico, all is okay?
Yes.
Okay, great. Now C. Now question C is studied French or German? French or German? Please, you can read also in our books. Maybe I don't remember if I mentioned it explicitly anytime.
Yes, we saw it once in the truth table.
Yeah, exactly. So actually, if you consider, if you have to find this or French unit is our union, F or G, correct? But if you simply add 25 and 20, you calculate the intersection 2 times. So the general formula is following: quantity of F plus quantity of G, and to restore the balance, you have to subtract 1 time the quantity, the power of the intersection, F and G. Is it clear? Because if you simply add F and quantity of G, you calculate the number of students which are inside the intersection 2 times. 2 times. So to restore the balance, you have to subtract 1 time the power of the intersection. If the intersection is 0, so you don't change, simply F plus G. But if you have non-zero, non-empty intersection, you have to do that. So according to our formula, we have 25 plus 20 minus 5, correct? So it will be 40. 40 students altogether studying or French or German. Or French or German. Any questions or doubts? All clear? No, it's right. No, 64 will be 35. Right? Yeah, because here this 40 includes both 5 students who study both languages, French and German. So if you want to find exclusive OR, in this case you have to subtract once again the number of students who study both languages. So it would come to 35. Is it clear? And finally, D, studied neither languages. D. But it means, of course, that we have to find U minus F or G. Correct? U minus F or G. It's the same as the complement of F or G. F or G. But you can now include you can use the De Morgan rule. We have it means complement of F intersection with complement of G. Yeah. And how we find this number? By the way, they may have intersection. So we have actually 2 ways. Because F or G occupies 40, so we simply find it's equal to 50 minus 40, or 10. Or 10. This is 10. Okay. So we have the 10 students studied neither or French or German. Any questions or doubts? All clear? Okay. Start in Mexico, is it all clear?
Yes. Yes.
Great. Now let's come to the next exercise. This is a kind of syllogism. Determine the validity of the following arguments. We have the premise S1. All my friends are musicians. S2. John is my friend. And S3. None of my neighbors are musicians. Can you conclude that S, John is not my neighbor? I will upload this file also to the Blackboard today. Is it true or not?
Yes.
Yes, because all my friends are musicians. John is my friend, so it means that he is necessarily a musician. However, if John were my neighbor, then it could not be musician, according to S3, because none of my neighbors are musicians. So if John were my neighbor, he would contradict of him being a musician. So it means that indeed John is not my neighbor. By contraposition, I can prove that. Because if John were my neighbor and none of my neighbors are musicians, so John could not be a musician. But we know that John is his friend, and all friends are musicians. John is a musician. Is it clear?
That is how you want us to write the solution.
You mean with formulas? No, you can use simply by words, yeah. Well, if you wish, it's possible to do, but it's first order logic. It's not so easy. You have to put for all x, all my friends, musicians, x. Yeah. But you have to define 2 variables. X are my friends, or even 3. X my friend, Y musician, and Z my neighbors. But not very easy, actually. I have 3 variables here. X is my friends, Y musicians, and Z neighbors. Yeah, but this simple syllogistic argument allows you to prove that first 2 S1 and S2 imply that John is musician. However, S3 and the assumption that John is my neighbor proves contradiction. So indeed, John is not my neighbor. Any questions or not? Let us see how we do it. Yeah, we can also simply without formulas. By the way, this Venn diagram also can help you a lot. So this diagram shows, do you see this diagram, yeah? It can also help you a lot. So the large circle is musicians, all musicians in the world, for example. US universe, all objects in the world. The friends are the circle inside musicians. Yeah, of course, usually it doesn't coincide because the number of musicians is much greater than the number of his friends. And also neighbors are beyond the greater circle of musicians. So neighbors are beyond. So neighbors have no intersection with my friends. And John is my friend, yeah. Or neither is musicians, and John is also. So it's proof that actually John cannot be in the third circle, which is beyond the circle of musicians and of friends. Okay. Yeah. By S2, John belongs to a set of friends, which is joined to a set of neighbors. S is a valid conclusion, and so the argument is valid. Okay. Now, the next exercise. Exercise related to relations. This also included all the first 2, 3, even how many? Even 4. The first 4 I included in the first topic, set theory. Yeah, so second topic, relations. Exercise 2 Roman 1 Arabic. Determine when a relation R on a set A. In a set A means that actually R belongs to A's direct product to A times A. Yeah. Not reflexive. Not reflexive. Let's write down by the formulas. By the way, you can use the formulas of first order logic with exist, always. By the way, I think we should also combine with gaining. So who would like to try to solve this exercise together with my help? Yeah, please do it. So first, not reflexive, then non-symmetric, non-transitive, non-antisymmetric. Okay. So let's do it. Let's switch to the. Okay, first, not reflexive. Let's first recall, to be sure, what we denied. We should recall what is reflexive. So we have a relation R. But first, let's decide what is reflexive. First, let's write down that R is actually R is simply a subset of A times A. Yeah. So actually R is some subset. R is a subset. You remember this, like not inclusion, but like this. A times A. A times A. That everybody sees. Okay, A times A. Okay. When we say that A is reflexive, when the diagonal, diagonal belongs to R. So R of A comma A is always true, yeah? So simply we put dot, first we put R of A, you remember we have several ways to write it, or R, and then in parentheses A comma A, A comma A, yeah? We omit true, it's simply, if you put R, it means it's true. If you put not R, it means false, yeah? So RAA is true. Or another way, remember, simply first RA without parentheses, A small, then RA. Comma. A, R capital, A also. This is also form of writing that R of AA is true. Yeah. And please remember, reflexive means that this is true for some A or for all A. Yeah, please put for all A small from A. From A small from A. Correct. Now you have to write the negation of this. So let's write it correctly. You always for all starts the formula. So for all A, for all A small, from A here, then put R of AA. So, but we are, please remember, we are now defining the vice versa, not non-reflexive, but reflexive property of reflexivity. Yeah? This is reflexive. So, not reflexive will be the denial of this property, negation, the negation. How we can obtain negation using the Morgan rules and others. Now let's negate this, negate. So now put it, not reflexive, let's put it like this. So this was reflexive and not reflexive. Put it now, not reflexive. Exist, correct. Exist at least one A small from A. Such that yeah, so negation of RAA. So not RAA, correct. That's it, absolutely true. Any questions or doubts? By the way, no, usually people don't put this signs of column because if you put, usually it's omitted, it's below. Simply exist A, not RA. This is right again in shorter form. So exist A, and then simply, not without belonging. Exist A, R, not R, A. Let's write once again without this. So exist A, not R, A. This is the complete correct form. Any questions or doubts? All clear? Great. Now, not symmetric. First, let's recall what is symmetric, vice versa. What is when we call the relation symmetric? Yeah, symmetric. So let's recall. What does it mean? Again, for all, now we can start from the beginning. For all A, B, here it's necessary to use different letters because at least two elements of A must participate. For all A, B, for all A, B, yeah, I mean from A capital, yeah, from A capital. What we have? That, so if RAB, then, so we have implication. RAB implies, no, you put R, you forgot R. After for all, you put R, no, please erase it, and put again. For all AB, for all A, B, R of AB implies what? R of BA, exactly. So it means that our region R is symmetric with respect to diagonal. If you consider diagonal, so if you have a point beyond diagonal, you have the symmetric point below the diagonal, and vice versa. Below means above. Okay, now you had to put the negation using the property. Now, not symmetric. What does it mean, not symmetric? Not symmetric, yeah. So, exists a pair, yeah, exists at least one pair, so AB, such that, again, remember, how we decipher the negation of implication. Implication can be deciphered as not premise or conclusion. But negation will give you premise and not conclusion, correct? So we have in this case means that RAB, and what? Not RBA, exactly. So for AB we have the relation, but if you change the order, you fail. Relation is failed. Absolutely correct. Does everybody see here? Estado de Mexico, do you see okay?
Yes. Yes.
Any questions or doubts?
No, at the moment.
All clear?
Yep.
Yes.
Great. Sorry? Okay. Now this was number 1, 2. It was AB. AB's. It was AB. Okay. I put better A and B, and now C. Now C. Not transitive. But let's again, as usual, first recall how we can express by logical formulas the transitivity of the relation C. First, let's write down what we mean by transitive. So here again, remember, but now it's more complicated because we consider triples. For all triples ABC, small from A, for all ABC from A, no, it doesn't matter, okay, I understand. What conclusion must be? So if we have RAB and RBC, it must imply what? So they conjecture, conjunction RAB and put and RBC must imply what? R of AC. So we can omit the intermediate term B, RAC. Okay, this is transitive. Now let's write the expression for non-transitive. Not transitive, negation. Not transitive. That exam is not too difficult. Simply we have a lot of questions. many questions. But I hope 3 years will be of 3 hours. Yes, not too long time. 3 hours will be enough. By the way, about the time, I remember this joke exactly related. Sometimes also in our countries, there's some people are considered like joke, like Galicia's Gallegos aquí. So they say we have some jokes about some people in Russia, Ukraine, for example, especially about Chukcha, the people who live in the Alaska, almost in Alaska, in front of Alaska. That one Chukcha said to other Chukcha, you know, I bought how to say this cassette. When you put this, you have to collect these units, put them in together, combine to have this not shuttle, but it's rifle, not rifle. Shared. When you combine these small pieces, combine the picture, for example, this is for children.
Like a puzzle.
A puzzle, yeah, exactly, puzzle. I have bought a great puzzle for 5,000 elements, and you know, I have managed to collect it for only 3 months.
Yeah.
What? And why are you so proud? Because it's written on the box that from 3 to 5 years. I have collected only for 3 months. So I think 3 hours will be enough for our problems. 3 years. Okay, now let's dig in.
He was busy, he had to go to work.
Yeah, only 3 months. For example, exists a triple, exists ABC. So now the negation, ABC. And now again, here we have implication. How we negate implication? Again, so we have our premise intact. So R of AB and R of BC, but simultaneously BC, and again and because remember, the implication itself it's phrased as or negation of premise or, but now we have negation. So and not RAC. So AB and BC is true, but not AC. Not AC. Correct. Is it clear to everybody? So we have a complete conjunction. Three properties. R of AB is true, R of BC is true, but not RAC is not true. Okay? And finally, not antisymmetric. Number D. Not antisymmetric. I remember, now let's recall what is antisymmetric. Antisymmetric is typical property for example, less or equal or greater or equal relation. So if you have A less or equal than B and B less or equal than A, it implies that A is equal to B. So remember, we have the following. So for all AB, the conjunction that R of AB and R of BA and R of BA implies that A is equal to B. So only one way. If we have A less or equal than B and B less, it's only way out is A equal to B. So this is typical for inequalities and other order relation. Okay. Now this is antisymmetric. Now let's write down what means not antisymmetric. Not antisymmetric. So it's typical property of order in relations. So only one way. If both ways, it means they sum the same number. Okay, not antisymmetric. So please take the negation. Again, exists at least one pair AB. AB. And again, we have the negation of implication. So again, we keep the premise intact. So RNB and RBA, and the negation of equality. So A is not equal to B, and A is not equal to B. That's it. Any questions or doubts? All clear? Great. Thank you so much for your participation. Let me mark your participation. Just a moment. Where is your list? Nobody took my list. No, this is here. Okay. Please recall your name. Arturo Silva. Okay, thank you. Okay. Now we switch to the next exercise. Maybe you can take a picture here. Okay, now an exercise. It's a bit more complicated because now we have to give examples. Give examples of relations R on the small set A, only 1, 2, 3. 1, 2, 3. Having the stated property. So A, property A. R is both symmetric and antisymmetric. It's quite important, interesting exercise because it allows you to understand that actually seemingly contradictory to each other properties may be realized on the same relation. Both symmetric and antisymmetric. Who would like to propose any relation? I leave it. Very calm in English style. For statement, don't worry, we are simply laughing that one student left by English style. Now say goodbye. Okay, so yeah, please do. Yeah, so Diego, please, let's work together with you. Yeah, sure. Okay, so it must be symmetric and anti-symmetric simultaneously. Actually, it's not very difficult if you remember. That. First of all, you must remember a very simple thing. In all definitions of symmetric or antisymmetric operators, we always have premises, assumptions that something happens. For example, if 1, 2 belongs to this relation, then also 2, 1 must belong. Yeah. For example, 1, 2, simply 1, 2 cannot belong. Also 2, 1 also must belong. Yeah. However, if there is no premises, remember the implication also is valid. So, for example, the empty relation is a trivial example of such relation. It is neither symmetric nor antisymmetric. I mean, vice versa. It's symmetric and antisymmetric because actually we have no any pair. For example, we say how to prove it's symmetric. Assume this not symmetric. It means there must be some pair. For example, 1, 2, but 2, 1 does not belong. However, we have no pairs at all. So by contraposition, it is symmetric. We're not speaking about anything. Or antisymmetric the same. We have to have two pairs. For example, 1, 2 and 2, 1. And nevertheless, A is not equal to 1, 2 must be equal to 1. It does not happen, but because we have no pairs at all, it also is antisymmetric. By the way, it's not only this is true, but also we can see that we have some other examples. For example, select 1, 1 and 2, 2, and explain why it is both symmetric and antisymmetric. Yeah, so select. Yeah, only 2 elements, 2 pairs, 1, 1 and 2, 2. And please explain why it's both symmetric and antisymmetric.
Well, symmetric says there is an A and B.
For all A and B, yeah. If AB belongs to our relation, then BA also must belong. Now let's see. Again, here we have if. This is the very easy point where we have obtained this some seemingly paradoxical results. Indeed, 1, 1 belongs to our R. Yeah. But if we change the order, we have again 1, 1. So again, if we change the order, 1, 1 does belong. So no problem. 2, 2. Also, we have 2 and 2 both belong. So 2, 2 belongs. Change the order. We have the same 2, 2 also belongs. You could even add 3, 3. Doesn't matter. It also obtains the same. Yeah. So it's symmetric. Everything is symmetric. Now, why it is anti-symmetric? Remember again, definition of anti-symmetric. So for all pairs, if both AB belongs and BA belongs, so A must equal to B. Now here we have the same. Yes, indeed. 1, 1 belongs, and if you change the order, this once again 1 belongs, but 1 is equal to 1 is no problem, no contradiction. The same is 2. 2, 2 belongs. Change the order again, 2, 2 belongs, and 2 equal to 2. So this relation is indeed both symmetric and anti-symmetric. So once again, these critical, simple, paradoxical results can be very easily obtained, especially if you include only few pairs. Few pairs. Yeah.
1, 2, and 2, 1.
No, in this case, it would be if you include, for example, 1, 2 into 1, it would be symmetric, but not antisymmetric. Not antisymmetric, because 2 is not equal to 1, although both belongs. Okay, now let's consider case 2. Case 2. Case 2. Neither symmetric nor antisymmetric. Neither symmetric nor antisymmetric. Now case not symmetric and also not antisymmetric. Now let's please again maybe show you this example and try to apart from empty set, of course empty set also, but let's explain why these are this list 1, 2, 2, 1, and 2, 3. We have 1, 2, 2, 1, and 2, 3. Why it's both non-symmetric and non-antisymmetric? Why is so? Yeah. Yeah. Why first? Why it is not symmetric? The question is evident, yeah? Because it includes 2, 3, but not 3, 2. 3, 2 is not included. Is it clear? However, why is it not antisymmetric?
Because there are no
No, actually, because no. Here exactly, it contains both pairs, 1, 2 into 1, but 2 is not equal to 1. Exactly, because we have 2 pairs, 1, 2, and 2, 1 included. But according to antisymmetric, it must imply that 2 is equal to 1, but 2 is not equal to 1. Correct? Yeah, so it's antisymmetric. Okay, and the last one, an example of R, which is transitive, but the union of R and R negative 1 is not transitive. Example is very simple. Select R contain only one pair, 1, 2. Let's explain this 1, 2. This pair, this R is transitive, but the union this inverse is non-transitive. Why is it transitive? By the way, once again, this simple example of playing on the non-existence of a triple. We have no triple. Only 1, 2, and that's more. So we have 3, you must have also 1, 3. But we have no any other pair starting with 2. So nothing of talking about, yeah? I mean, this is the solution. This R is only 1, 2. This explains why this operator is transitive, but its union with inverse is non-transitive. So once again, it is transitive because there is no triples. Not again. You could let's prove that it is not transitive. We immediately fail because if you prove of transitive, we have to select 2 pairs, AB and BC, such that RAB, RBC, but not RAC. But we have no triples. Only one pair, 1B, 1, 2. So we have nothing of talking about. Our try to prove by contradiction fails. So this, speaking formally, it is transitive. Trivially, but transitive. However, you remember, what is R negative 1? It's simply the pair 2, 1, yeah? 2, 1. If you unite these 2 pairs, 1, 2, and 2, 1, why it is not transitive? If you unite 2 pairs, let's consider now R union with R negative 1. Union with R negative 1, it will be 2 pairs. 2 pairs. It will be 1, 2, and why this relation is non-transitive? Because to be transitive, it must include each pair. 1, 1, exactly. Because from 1 to 2 and from 2 to 1, it must contain 1, 1. But it does not contain 1, 1, so it is non-transitive. Is it clear? Just a moment. Yeah, also 2, 2, correct. So actually to include 1, 1 and 2, 2. If you collect it also contain 1, 1 and 2, 2, it would be transitive. But it doesn't contain 1, 1, neither 2, 2. So this is non-transitive. So that's a good example that relation may be transitive, but its union with R negative 1. By the way, R negative 1 also is transitive. It's also transitive because only 1, 2, only 2, 1. Also, we have no triples. Also transitive. But the union of two transitive may be not transitive. It's quite often paradox can be seen. Is it clear? So let's see why it's not transitive, because to be transitive it must also contain 1, 2, 2, 1, so 1, 1. But also 2, 1 applied to 1, 2 must contain 2, 2. But it doesn't contain, so it's non-transitive. By the way, but this is transitive, this is also transitive. Please put parentheses. Please put here parentheses.
Professor, can we see
Now, let me please show, just a moment. To finish, let me please show you the paper. Yeah, so to explain the last example, let's explain once again this C. So why R, for example, 1, 2 is transitive? Why R equal to the only containing one pair, 1, 2, why it is transitive?
Because we don't have a C to pass through.
Yeah, because we have no any other pair, for example, starting with 2. So nothing of talking about, so it's formally it's transitive. The same is for R negative 1, 2, 1. Also contain one pair, and no pair of 1, for example, 3. So again, nothing talking about. However, if you unite these two, relations, you obtain relation containing 2 pairs, 1, 2, and 2, 1. And this relation is already non-transitive, because to be transitive, it also must contain 1, 1, so through 2. 1, 2, 2, 1 must contain, and vice versa, 2, 1 through 1, 2 must have 1, 1. So 2, 2. So if we have no 1, 1 and 2, 2, this relation is non-transitive. Is it clear? Clear or not?
Yes. Yes.
Okay, so thank you for attention. Once again, on now our next session will be present in Ciudad de Mexico. The first day, 15th of October, we'll try to pass all topics of statistics we are going to include. And the last hour of our class of Monday from 6 to 7 we devote to continue solving the draft exam, hoping to finish solution with all including statistics. If you finish statistics, then we include it in the exam. If not, if you stop after probability, then we don't include in the exam on Tuesday 16th. Okay, thank you once again, everybody. Yeah, sure. And see you on next Monday. I will open the assignments for homework 2.4 and 2.5. I have 2. Sorry? Yeah, I will upload now. The upload is fine now. Okay, so have a nice fortnight and see you again.
Bueno, te lo que cabe
Last part of the